For part 2 of Chapter 9 lecture, we'll talk about upper atmosphere winds, or as they're called, winds aloft. And these are winds that are in the upper atmosphere. And we start by looking at the intertropical convergence zone, which you remember is the area, the band around the equator, which migrates north and south depending on season, where we have convergence. So we have winds blowing in, and because they pile up here, they rise up. We have low pressure around the equator and stormy conditions because of all the moist, uprising air that can produce very strong thunderstorms. So when we continue this circulation pattern that you see in the red here, there's convergence at the surface, uplift, and then the air spreads out. We have divergence aloft. And so we have these convective cells here, and remember this is the Hadley cell circulation. So we have this transport of this warm equatorial air that drifts in the upper atmosphere poleward in the northern and southern hemisphere, and then it starts to sink or subside around 30 degrees north and south latitude, and the other circulation that we saw begins to kick in. When we look at middle latitudes, so away from the equator and away from the pole, in between there, we have winds that are blowing from the west to the east in a wave-like pattern of ridges and troughs that defines what we'll see is the jet stream. So when we look at what's happening here, this is where the polar lows meet the subtropical high, and this strong difference between cold polar air and warm tropical air causes very strong pressure gradients and this flow pattern that is responsible for moving a lot of the weather through the middle latitudes. So when we have this clash of different air masses, we have the formula we need for weather. And so we have, again, this poleward transport of warm air and some of this cold air making its way back down south in the northern hemisphere. If we take a look at surface ocean currents, we have a similar pattern in the ocean currents as we have from surface winds. At the surface, the ocean's currents are driven by the wind. So we have a large-scale movement of ocean water that mimics the large-scale atmospheric circulation. And these large circulations in the ocean are called gyres or gyres. These are big circulation regimes that we can see when we look at a map of world ocean currents. So let's take a look at one of these maps, and we see here in the Pacific Ocean off the west coast of the United States and extending over to Asia, we have a big gyre here that is transferring air in the atmosphere. The atmospheric circulation around this subtropical high is mimicked in the ocean currents that we see here. And you'll see as you look through here, the same types of patterns occur in the ocean currents as we saw in part 1 occur for the larger scale atmospheric circulation. You may have heard in the news this past year about a trash island or a trash vortex, and this is garbage that gets dumped into oceans and ends up getting caught in these gyres, and so it just kind of spins around, it circulates around the ocean, and as it does, it breaks up a little bit. Plastics break up, but they don't really disintegrate in the sense of they just vanish. They break into tiny little particles that introduce toxins and dangerous things that fish in the ocean can eat. So here's a YouTube website, or sorry, a Greenpeace website that we can visit. So here's a Greenpeace website that you can visit that explains more about this issue if you're interested. So if we look at waves in the westerlies, we have this upper air current that I talked about a moment ago. And when it's behaving itself, let's say, we have what's called zonal flow. So something like you see up here, where the winds are blowing kind of parallel to the lines of latitude. And this is called zonal flow. And then in a more extreme situation, when we have winter, for example, in the northern hemisphere, where we can have this cold air drop way down and then the warmer air kind of wedge its way in between, we get what's called meridional flow. And meridional flow is almost vertical, right? It's almost flowing parallel to the lines of meridians, the lines of longitude. That's where it gets its name from. And so this is something that happens with this dance we have between the polar low and the subtropical high, with this cold air and this warm air. It's always erratic. So sometimes it's flowing this way, sometimes it takes a dip, and we have these troughs and ridges that really cause a lot of weather to happen for us in North America. So it makes it really challenging for long-range forecasting, because it's really hard to forecast what this is going to do. So here's an example of something that can happen. We get what are called blocking systems, and we've seen this in North America. And this happens when we get strong meridional flow in the jet stream area here in the westerlies, and it's so strong that we can have this little breakaway system. So this little pocket of cold air kind of breaks away from the main flow of this polar low, and then we get this warm air that gets stuck in a circulation pattern in between there. So instead of having a constant kind of flow, we get these little subsystems that are created, and they kind of block the usual flow of air. And we see some examples here where we've had extreme weather events because of this kind of weather dynamic. In the top picture in A, this is from 1988, which some of you may remember, some of you may not. There was a severe drought, and the drought was caused in part, it was in the summer, it was caused in part because of this breakaway pattern that we had with this high pressure cell, here, and it just kind of camped out over the central part of the United States. And high pressure, remember, causes stable air. We have sinking air, so there's not really any chance for thunderstorm development, and very, very little chance of rain. So things dry out, and that's what happened. So very severe drought that took place at that time. Another example, well, before we jump into that, this picture down below shows a more average circulation pattern, so you can compare what was going on in the summer of 1988 to what's more average. And you see, yeah, there's high pressure, but we don't have like an individual high pressure cell just camped out over the United States. We have this flow of winds in motion. Here's another example of one of these blocking systems that happened in 1993, again in the summertime for us in North America, in the Northern Hemisphere. Here we had a high pressure system that was camped out kind of over the southeastern portion of the United States, and the jet stream was kind of dipping down a little bit, so we had this play between these two contrasting air masses. And the circulation around this high is, of course, clockwise, so the winds that were coming up to the middle where this green arrow is were warm, moist winds, or warm, moist air that swooped up on the western side of this high pressure system and met this area where the jet stream is and caused a lot of precipitation. So there was severe flooding, record flooding in the Midwest, and drought again over the southeast, because it's more in the heart of the high pressure cell where there's not going to be any chance of precipitation. So the jet streams are very fast moving air currents that are like long rivers. Because they're so high up in the atmosphere, they are not bound by friction of the surface, so they can flow very fast. The speeds get up to over 200 miles per hour. In the northern hemisphere, our primary jet stream is what we call the polar jet, like we saw in the previous slides. It's the boundary between the subtropical high and the polar lows. It forms at the tropopause between the troposphere and the stratosphere, and right at that boundary where the cold polar air meets the warmer subtropical air. And it's these differences in pressure and temperature that cause severe pressure gradients and allows the jet stream to really be created at all for that fast-moving air in response to these steep pressure gradients. Here's a picture of the jet stream. You can see it kind of sits right around that boundary between the subtropical high and the polar lows, and it's responsible for driving the weather in our country, in the United States. Here's kind of a cross-section as we look from the North Pole over here on the x-axis on the far left, and we make our way south to the equator. And what we're really looking at here is the position of the jet stream. And here's the height of the tropopause. So the troposphere is much thicker where it's warmer. So if we were to measure the depth of the troposphere at the equator, it's much deeper than it is at the North Pole, and we see this continuous decrease as we move poleward. Where these big J's are represent the jet streams. So right at about 30 degrees north latitude, we have the subtropical jet, and then the polar jet that I just mentioned is right around 60 degrees where the cold polar air meets the warm subtropical air. The subtropical jet is responsible for some of our weather, more in the southeastern part of the state, but it's not as strong, it's not as sharply defined as the polar jet. So the jet streams are definitely, they vary with seasons. So in the winter, both of the jet streams become much stronger. And here we're seeing the polar jet. So in the summer, it's pretty far north, right? It's retreated because it's northern hemisphere summer. Things are warm, so all that cold air has retreated further north. In northern hemisphere winter, when the cold air comes back down, that jet stream can be as low as you see it in this blue line here. Typically, it's kind of like right in the middle here, but we can get these big dips that dip way down. The subtropical jet stream is found just on the pole side of the Hadley cell, that first circulation cell from the intertropical convergence zone, and where it begins to subside around 30 degrees north and south latitudes. So as we saw on the previous slide, there's the break in the tropopause there, and it allows for this jet stream. It also is stronger in winter, and it's less variable with latitude than the polar jet stream is. It doesn't have those erratic rises and sinks, troughs and ridges like we see with the jet stream. Okay, that's the end of part 2.